Imagine a clock so precise it can sense the faintest tremor in the fabric of space-time. A tremor caused by something invisible, something that holds our galaxy together. Dark matter. Dark matter is a cosmic ghost making up most of the universe's mass, yet it's completely unseen. How do you find something that doesn't want to be found? You don't look for it, you listen for its whisper, using a clock sensitive enough to hear it. This is not science fiction. This is the cutting edge of discovery. We've built telescopes to see distant galaxies, particle accelerators to smash atoms. Now we're building a nuclear clock. Its purpose? To alert us to the universe's greatest mystery. If dark matter interacts with the fundamental forces of nature, even weakly, it should cause tiny, almost imperceptible fluctuations in those forces, fluctuations that affect the flow of time. Think of the universe as a still pond. Dark matter is the invisible breeze, and the nuclear clock is our instrument to detect the ripples. This clock stands guard over the constants of nature, waiting for a sign that they're not so constant after all. Our journey begins with thorium-229, a radioactive isotope with a unique energy transition, an atomic-scale metronome of unprecedented stability. By harnessing this, scientists are building not just a better clock, but a new way to perceive the universe. They're learning to see with time, not light. If we succeed, we won't just find dark matter. We'll prove that the laws of physics can be gently bent by the unseen architecture of the cosmos. The clock is ticking, and the universe is waiting to tell us its secrets. This is a story about time, a ghost, and the human drive to know. The nuclear clock is our sentinel, listening for the faintest whisper from the dark. With every tick, we get closer to unveiling the invisible. The universe's secrets may be written in time itself. Atomic clocks have long been the gold standard of timekeeping, tracking the oscillations of electrons as they jump between energy levels. These clocks are why GPS works and our networks stay synchronized. But electrons, sitting on the atom's edge, are exposed to interference, like trying to hear a pin drop in a noisy room. For most uses this isn't a problem, but to hunt dark matter we need near absolute precision. Enter the nuclear clock. Instead of electrons, it measures oscillations deep within the atom's nucleus, a fortress shielded from outside noise. The nucleus, made of protons and neutrons, is far less susceptible to disturbance. A nuclear clock is fundamentally more stable. The challenge? Exciting a nucleus usually takes immense energy, like moving a mountain with a feather. For years, a practical nuclear clock was just a dream. But if scientists could find a nucleus with a gentle, low-energy tick, they could build the most precise clock ever. The search was on for a special atom, one that could unlock the next era of timekeeping. That atom is thorium-229. Thorium-229 is unique. It has an exceptionally low-energy excited state, the gentle tick scientists sought for decades. Most nuclei are like heavy bells, needing huge energy to ring. Thorium-229 is a delicate handbell, rung with a tiny amount of energy, within reach of modern lasers. This low-energy transition is the nuclear clock's tick. Scientists trap a single thorium-229 ion, hold it still in a vacuum, and shine a precisely tuned ultraviolet laser to excite the nucleus. When the nucleus returns to its ground state, it releases energy at a frequency so stable it could keep perfect time since the birth of the universe and be off by less than a tenth of a second. The clock locks its laser to this nuclear transition, synchronizing technology with a fundamental constant of nature. This stability transforms the nuclear clock into a probe for reality itself. Any force that can reach the nucleus, like exotic particles or dark matter, could alter its tick. The thorium-229 nucleus becomes our ultimate sensor, waiting for a whisper from the cosmos. With this clock, we can detect the faintest changes in the universe's fabric. It's not just a timekeeper, it's a window into the unknown. The nuclear clock is ready to listen for the universe's secrets, and dark matter may finally have met its match. How does a clock find the invisible? The idea dark matter might subtly interact with the fundamental constants of nature. If dark matter is a diffuse, oscillating field, as some theories suggest, it could cause these constants to wiggle as Earth moves through it. The thorium-229 nuclear clock is exquisitely sensitive to such changes. If the strong nuclear force or electromagnetic force shifts, even slightly, the clock's tick changes. Scientists compare the nuclear clock to other atomic clocks. If a dark matter wave passes, the clocks go out of sync in a predictable pattern. By monitoring these clocks, we search for a phantom signal, a direct sign of dark matter. Time itself becomes our detector. Dark matter is one of science's greatest mysteries, a form of matter we can't see, touch, or detect with conventional tools. It doesn't emit, absorb, or reflect light, yet we know it's there because of its gravitational effects. Galaxies spin too fast for their visible mass. Something unseen holds them together. This invisible mass outweighs visible matter 5 to 1. We see its influence in gravitational lensing and the cosmic microwave background. But what is it? Leading theories suggest undiscovered particles like WIMPs or axions. Finding dark matter would open a new realm of physics, revealing that the particles we know are just a fraction of the cosmic zoo. Detecting it isn't just about missing mass, it's about rewriting the universe's instruction manual. The hunt for dark matter is a quest to understand the very foundation of reality, and the nuclear clock may be our best tool yet. What if the nuclear clock works? What if we detect a periodic stutter in time, a signal matching dark matter's predicted signature? It would be a monumental discovery, confirming dark matter's existence and giving us our first tangible clue about its nature. We could estimate its mass, its interactions, and guide other experiments to zero in on the culprit. Even more profound, if fundamental constants aren't constant, it would shatter our assumptions about the laws of nature. This could connect dark matter to other cosmic mysteries, like dark energy. A thorium-229 nuclear clock is so accurate it wouldn't gain or lose a second over the universe's entire age. Its mind-boggling sensitivity gives us a real chance to see time itself flicker, revealing the invisible world all around us. The universe's secrets may finally be within reach. For centuries, we explored the universe with light. Now, we're learning to listen to the rhythms of space-time itself. The nuclear clock is a stethoscope pressed to the cosmos, connecting the quantum world of a single nucleus to the largest mysteries of the universe. By measuring a tiny oscillation inside an atom, we probe the nature of dark matter, the force that shapes galaxies. The universe hides its secrets in the flow of time. Whether we find a signal or silence, our understanding of reality will be forever changed. Science advances by asking bold questions and building extraordinary tools. The journey is as important as the destination. So next time you look at a clock, remember, scientists are listening for a signal from the dark. The steady tick of a thorium nucleus may soon reveal the universe's deepest secrets. The clock is ticking, and we are listening.